video, we're going to talk about how to draw Lewis structures. And this is a little bit different than how I taught it in honors chemistry, but it's a much more effective way and faster with the type of compounds that we're going to have to draw the Lewis structures of. So we'll talk about first bonding pairs of electrons and lone pairs of electrons. Valence electrons are distributed as shared or bonding pairs of electrons, so that would go between the two atoms. So if we're looking here in HCl, our bonding electrons are the ones that make up the bond, and these that are showing up here are going to be your lone pairs, or we'll also call those unshared pairs of electrons. And both will have an effect on the structure. Alright, so we'll do the Lewis electron dot structure because it does involve the line that represents two electrons or one pair of electrons here and here that are being shared, and then the other electrons are the valence electrons of the other atom. So we have core and valence electrons. Really, in bonding, the reason why atoms act a certain way is because of the number of valence electrons. And that's why all the alkali metals act a certain way, and all the alkaline earth metals also act their own particular way. It's because of the number of valence electrons. And we can get that from the periodic table. Remember that most atoms want an octet, and we'll talk about the exceptions a little bit later, of electrons. Now, there are some, and I call them the little guys. Hydrogen, helium, lithium, and beryllium are okay with only two valence electrons. Because they are small, they don't have a whole lot of energy levels, and it only takes two to fill up the first energy level, and when they have a full energy level, it is considered stable. It's full or 8. Okay, so the way we're going to go about this, we're going to decide on the central atom. It is never, ever hydrogen, and it is never fluorine. It's very rarely a halogen at all. It is carbon if present. And the central atom is the one that has the lowest affinity for electrons. Generally, that's going to be the first one written in a formula. That will be your center atom. Then what we're going to do is we're going to calculate our happy. Happy is the number or the amount of electrons each atom would like to have in an electron count. And we'd also like to have our have electron count, and that's the amount of valence electrons each atom has. We'll do a couple of little calculations involving happy and have. Happy minus have divided by 2 is the number of bonds. And then you can find the number of electron pairs that you have to work with, and that's have divided by 2 is the number of electron pairs that you have to work with. You draw your bonds between the central atoms and each surrounding atom, and then the remaining electrons, the ones that aren't bonds, so it's going to be the number of electron pairs minus the number of bonds, tell you how many unshared pairs or lone pairs are needed to complete the octets. And you're always going to start with the outside atoms first, and if there are any remaining lone pairs, then they will go on the center atom. So let's try that. We're going to start with ammonia. So first we're going to do our happy, and then we'll do our have. So in ammonia, I've got nitrogen and I have hydrogen. Nitrogen would like to have 8, and hydrogen, there are 3 of them, it would like to have 2 to be considered stable. And so 8 plus 6 is going to give me 14. Have. Nitrogen from the periodic table has 5 valence electrons, and each hydrogen has 1 valence electron. Again, I got that from the periodic table. So 5 plus 3 is 8. So happy minus have gives me 6, divided by 2 tells me that I need to have 3 bonds. All right, so happy minus have divided by 2 gives me the number of bonds. If I take have and divide it by 2, it tells me the number of electron pairs. So 8 divided by 2 is 4 electron pairs. So now I'm going to write these. Nitrogen is the first one written in the formula, so it's going to be my center atom. And I need to make 3 bonds, and I have 3 hydrogens here. So I'm just going to go ahead and link those. Those are my 3 bonds. I only have 1 more electron pair to deal with. So I have 4 electron pairs total, minus the 3 that are in bonds. That gives me 1 remaining electron pair. And that is going to go on the outside atoms first. But hydrogen only has 1 energy level and cannot hold any more electron pairs. So I can't put them on any of the hydrogens, so it has to go on the center atom. And so that is the Lewis structure for ammonia. All right, we'll practice this a little bit more. I think I go through this in excruciating detail. About this. Okay, so let's talk about what if it is a polyatomic ion where it has a charge. This one has 2 extra electrons, sulfide ion does, because of this S2 negative, and so we must take that into account when we're drawing our Lewis structures. So the central atom is going to be sulfur because it is the first one written. So we're going to do happy minus have, or happy have, happy and have. I have sulfur and oxygen. So for happy, what I'm going to do, sulfur would like to have 8 electrons. Oxygen would also like to have 8, but I have 3 of those oxygens given by the formula over here. So happy is going to be 4 times 8, 32 electrons. So for have, sulfur has 6 electrons, and oxygen also has 6 electrons. I have 3 of those, so then it's 4 times 6, that's 24. We're also going to add in these extra 2 electrons to the have only. So that gives me 26 there for the have. So happy minus have is going to give me 6. 6 divided by 2 is 3 bonds. Again, happy minus have divided by 2 gives you the number of bonds. Have divided by 2 gives you the total number of electron pairs we have to work with, and that's 13 electron pairs. So then we need to draw this. Sulfur is going to be my center atom, and so I need to have it bonded to 3 oxygens, and I have 3 bonds, so I'll just go ahead and put those on there. I have 13 pairs of electrons. 3 of them are in bonds, so I have 10 more electron pairs to work with. We're going to start on the outside atoms, and we're just trying to fill up their octet. So this oxygen already has access to 2, so it needs 6 more electrons, or 3 more pairs. Now I'm down to 7 electron pairs. This oxygen, again, is going to need access to 8 electrons, and so I've used up 3 more there, so that's going to give me 4 electron pairs remaining. This oxygen that's over here also needs to fill up its octet, and that used up 3 more pairs of electrons. Oops, 3 more pairs of electrons, so that gives me 1 more. I have no other place to put that unshared pair of electrons, so it has to go on that center atom, and this is the structure for the sulfite ion. Now we're going to try carbon dioxide. Carbon dioxide, we'll do our happy have for that one, and happy and have electron count, I've got carbon and oxygen. Happy, carbon would like to get 8, so would oxygen, but again, I have 2 oxygens, so that's 3 times 8, that is 24. For my have, carbon has 4 valence electrons from the periodic table, and each oxygen has 6 valence electrons. So it's 12 plus 4, that gives me 16. Happy minus have is 8. 8 divided by 2 gives me 4 bonds. And then I have half divided by 2 gives me the number of electrons that I have to work with, and so that's going to give me 8 electron pairs that I have to work with. All right, center atom's always going to be carbon if carbon is present, and I have 2 oxygens, and they are going to try to be as far away from each other as possible, but we'll talk about that when we get into VSEPR. I'm going to make 4 bonds, so since I only have 2 things to bond to, they're going to have to be double bonds. Now I'm going to need to deal with my extra electron pairs. I had 8 electron pairs, 4 of them are in bonds, so that means I have 4 remaining electron pairs to work with. So I need to work with my outer electrons and have them get an octet of electrons. So this oxygen here on the right has access to 4 electrons already in the bond, and so it needs to have access to 4 more. So there we go. So that takes care of 2 electron pairs. I only have 2 more. And so the same thing's going to happen over here to this oxygen. That uses up all my electron pairs. I don't need any on that center atom. Double and triple bonds, so those multiple covalent bonds, are commonly observed for carbon, nitrogen, phosphorus, oxygen, and sulfur. So if you see any of those in a formula, you just want to be suspect that there may be a multiple bond there. And you can remember CNOPs. I don't know. Those are the ones that multiple bond. Now let's look at sulfur dioxide. We'll try our happy have. So happy and have. Happy for sulfur and oxygen. Sulfur would like to have 8, and so would oxygen. I do have 2 oxygens as given by the formula, so my happy total number of electrons would be 24. Have for sulfur it's 6, and it's also 6 for oxygen, but again I have 2 of those oxygens. So 3 times 6 is going to be 18. Happy minus have, I end up with 6. Divided by 2 gives me the number of bonds, which is 3 bonds. And then have divided by 2 tells me the total number of electron pairs that I have to deal with. So I have 9 electron pairs that I'm going to be dealing with. All right, so sulfur is going to go in the middle since it's the first one written, so we have sulfur there. And now I have 2 oxygens around it. So I'll put one here, and I'm going to put the other one over here. I have to make 3 bonds, but if I link up all of my atoms here in this molecule, I only use 2. So that means there must be a double bond. But which one has the double bond? The answer is both and neither. So I can put the double bond here, and that would deal with the number of electrons. Let's go ahead and finish this one out if I put the double bond there. Then I have 9 electron pairs to work with, minus the 3 that are in bonds. I had 6 more electron pairs that I have to work with. So I need to fill up the outer atoms first. So I have 4 here for this oxygen here with the double bond, and so I need to put 4 more on there, or 2 more pairs, to fill up that octet. Then we go to the oxygen here on the left, and it only has access to 2 electrons, so it is going to need access to 6 more, which is leaves me with 1, or it's 3 pairs, so it leaves me with 1 electron pair remaining, and so I do have to put an unshared pair on that center atom. So that's one possible structure. The other possible structure is very, very similar. It's just with the other oxygen getting the double bond. Since this double bond could go between this oxygen or between this oxygen, what we have here is a resonance structure. So anytime you end up with something like this, it is a resonance structure, and what we do is you draw both, or if there is more than 2, you draw all of the possible structures And you're going to put a double-headed arrow in between them. So if I had drawn this one over here. And just to show that what's actually happening here is it's not the first structure and it's not the second structure, but it's a hybrid of the two structures. It's almost like each bond has, or each atom has a bond and a half. But we can't really draw half bonds. So we just draw all possible structures with this double-headed arrow in between them. And again, that is called a resonance structure. So resonance structures, sometimes there's more than one valid structure for a molecule or an ion. Why don't you try and write the structure for, or draw the structure for a nitrate ion. You can pause this video, see if you can do it, and then I'll go over the answers. Okay, so you should have something like this. You have your happy, your have. Remember that you had to include your extra electron as indicated here by the charge on that molecule in your have count only. So happy minus have gave me 8 divided by 2. That means 4 bonds. And then have divided by 2 meant I had 12 electron pairs to deal with. So the first time I drew it, I put the double bond on the oxygen over here on the right. And then I had to put, after I drew the structure and added my remaining electron pairs to fill up the octet of the central electrons, I didn't have to have any unshared pairs on the center atom, nitrogen. But I do have to indicate that this particular compound does carry a -1 charge. And you do that by putting the square brackets around the completed Lewis structure and putting the charge out on how many extra electrons it has. So then I just drew it so that I have the double bond in different spots. So here I drew it so that the double bond was on the oxygen that I drew towards the bottom. And then in the third structure, I did put that double bond with the oxygen on the left. Double-headed arrows belong in between each of the structures, and I have each of them showing the notation for an extra electron to make it that nitrate molecule. Now, it's important to know that we use the double-headed arrows to indicate that it is an average of the structure. It is a hybrid. So it is not any of those 3 structures, yet it is all of those 3 structures. That double bond does not actually move. It's just the best way for us to draw resonance structures. So again, it is a hybrid of all of that. For nitrate, it's like each oxygen has a bond and a third as that molecule is drawn.